I'm here to, my name is Richard Townley. I am your humble secretary of the MAS, and I am here to talk to you today about the end of the universe. So, all the people who made the jokes about this really being the end of the universe, well, you're in luck. It's just a talk about it. But also, I'd like to say that, sounds good? Sound is good? Okay.
Say something.
Something. Okay, good. So, first of all, I'd like to say that my talk is not just about the end of the universe. I sort of gave it that title to get people to come here because it's exciting and all that. On the internet, they call that clickbait, but unlike those internet articles, I actually have something of substance to talk about here. So, but really, a more apt title, I suppose, would be a list of astronomical and astrophysical phenomena of interest that will happen between now and the end of the universe. But before we get started with that, let's first talk about a brief history of the universe so far. So, as we all know, the universe began with the Big Bang, which happened very, very quickly. And this was the first era of the universe, so to speak. It lasted about 1 picosecond, and that's 10 to the negative 12 seconds there, so it was over very quickly. I would say in the blink of an eye, but this is actually millions of times faster than the blink of an eye. And really, this subject deserves its own talk, because so much happens so quickly right here. At the very beginning, in fact, some of the physical laws that we now know may not have even been quite the same. We do know that some of the fundamental forces, like the strong nuclear force, the weak nuclear force, electromagnetism, things like that, they may not have been in play, and then they quickly came into being. But yeah, it was a very exciting and also very short time of the universe. So that was the first era, and it was over really before it started. Then after that, we had the early universe, which lasted about 377,000 years, this era did. And this was basically a period of time where it was right after the Big Bang. The universe was most of the size that it is right now, which is what happened in that very early time. It expanded very, very quickly and then slowed down also very quickly. And basically, everything was extremely, extremely hot at this point in time. In fact, so hot that atoms themselves actually couldn't really come into play. You had just a bunch of protons, neutrons, electrons, all just sort of floating around there in sort of a plasma. So it was sort of like an atomic soup for a little while. And so that lasted about 377,000 years. And then the third era of the universe was the dark era, which, as you can see, I chose to represent by just a dark slide here. This lasted about 1 billion years, and this was the point where things had cooled down enough that atoms could actually form. And there wasn't any light, really, because it had cooled down quite a bit, and galaxies and stars didn't come into play for a little while, as you can see, 1 billion years there. So there was some matter here, but not much was really happening until near the end of this. It started to congeal a little bit, and galaxies started to form, and in those galaxies, stars started to form. And that brings us to the fourth and current era of the universe, which is the stelliferous era, and it's still going on right now. This is what we're all familiar with. We have galaxies throughout the universe, and inside those galaxies, billions and billions of stars. And this is basically just where we are right now. So, where do we go from here? Well, there are three possible universe-ending scenarios that may or may not happen. The first scenario is called the Big Crunch, and this is the idea that basically the universe it's expanded quite a bit at the Big Bang, but maybe it might end up slowing down. The expansion might end up slowing down and then eventually stop and then start collapsing in on itself again. And it would keep collapsing faster and faster until eventually it sort of ends in a reverse Big Bang where it all comes together again, and then maybe another Big Bang comes off after that. That might happen. Or it could also be the Big Rip, which is a scenario where the universe, instead of collapsing in on itself, continues to expand. And in fact, the expansion gets faster and faster And it keeps expanding even more until eventually it basically expands so quickly that all matter is sort of ripped apart because it's expanding. It basically, on the atomic level, expands so much that atoms can't really stay together anymore. It could be that, or it could also be something known as the Big Freeze, which is basically where the universe would keep expanding, but not so quickly that it tears everything apart, like in the Big Rip. It would just keep expanding and just keep going on, and things would sort of slowly wind down, and entropy would increase just basically to the maximum, and it would sort of just end, and not much would happen for a very, very long time, and yeah, freeze, basically. So these were all three very popular theories, but only one of them really seems likely now. And it's not the Big Crunch, because as we learned in the late 90s, the universe is actually not slowing down. The expansion of the universe is actually accelerating. So it's actually expanding faster and faster. So that makes this scenario seem pretty unlikely, because if it was going to slow down and collapse in on itself, well, it probably wouldn't be expanding faster and faster. So that's probably not going to happen. And so since we know now that the universe is actually expanding faster and faster, well, doesn't that make the Big Rip seem pretty likely? Well, it did for a little while, but basically which one of these two will happen depends on the nature of dark energy, which is this mysterious force that we don't know much about that's causing the universe to expand like it is. And basically, if dark energy is very, well, energetic, to put it sort of mildly, then the Big Rip will happen, but if otherwise, it'll be the Big Freeze. Well, pretty recent observations have sort of ruled the Big Rip out as well, because we learned a little bit more about dark energy, and it's all really complicated, and I don't claim to understand any of it, but it looks like right now the Big Freeze is probably what's going to happen. So, what is going to happen between now and the Big Freeze? Well, before I start, I should say this list is a bit biased for the planet Earth, since we all live here, and there's a lot of events that'll certainly happen other places in the universe that we'll never get to see, but there are also a lot of things that'll happen here, especially to our own solar system, in the time between now and the end of the universe. So I'm going to include some of those, as well as some of the astrophysical things as well. But one thing that's going to happen between now and then is about in 10,000 years from now, the star Antares, which is the brightest star in Scorpius here, is going to go supernova. And it says 10,000 years from now, but actually what it should say is sometime, anytime in the next 10,000 years. We don't know exactly when it's going to happen, when it's going to go supernova. In fact, I kind of hope it does go supernova tomorrow, because that'd be really nice to actually see a supernova in our galaxy. They don't happen all that often. But when it does go supernova, it'll be very bright, of course. It might look something like this, and it might even be bright enough to be seen during the daytime, if it happens during the winter or something like that. But sometime in the next 10,000 years, that's going to happen. And about 36,000 years from now, the star Ross 248 will actually become the closest star to the sun, briefly. And by briefly, I mean for 8,000 years. But so as you can see here, this is a graph of basically which stars are going to be the closest to the sun. As you can see, there's right now, and there's Proxima Centauri, which is the closest one. Alpha Centauri not too far behind. And then as you see, as time goes on, Alpha Centauri will actually take over Proxima Centauri for a little bit. And then this star, Ross 248, will come in, and it'll be the closest star to the sun. And then it's going to go back out again. But for a good 8,000 years or so, it'll be the closest star to the sun. Then, in about 50,000 years from now, the current interglacial period of the Earth will end. So that'll send us back into another ice age. And this is going to happen regardless of the effects of climate change and regardless of global warming. We are going to go back into this the glacial, rather, period of Earth. And this is sort of an artist's impression of what glacial maximum looks like. And also, in 50,000 years from now, a day on Earth will actually be 1 second longer than it is right now. And that's basically because the moon is gradually slowing down the rotation of the Earth. And so 50,000 years from now, it'll be 1 second longer. And then in 100,000 years from now, the proper motion of the stars through the galaxy will basically mean that many of the constellations we now know will no longer be recognizable, or they'll look completely different. Like, for example, this is what the Big Dipper will look like in about 100,000 years from now. And so you can see someone's kind of bent the handle quite a bit more, and this doesn't look so much like a dipper anymore. But this is actually one of the better ones, because the stars are still mostly where they were. Some of the other ones, if you were to look at them, you'd see the lines going all over the place because they've just moved so much they're not recognizable at all. So about 100,000 years from now, that'll happen. And also, in about 100,000 years, it's pretty likely that Earth will have undergone a supervolcanic eruption. So some of you guys might remember hearing about the Yellowstone Supervolcano a few years back, and all the hype that generated. And it's probably, Yellowstone is only one of the supervolcanoes on Earth. It might be the one to go first, or it could be one of the few dozen others. But probably, and sometime in the next 100,000 years, one of these supervolcanoes will erupt, and of course that'll be bad for life on Earth, because when it does so, it'll throw up a lot of ash and soot into the atmosphere, which will make photosynthesis hard, and yeah, a few species might go extinct from that. Hopefully not us. But then, in about 500,000 years, or sometime in the next 500,000 years, it's pretty likely that Earth will have been hit by a 1 kilometer wide asteroid. And the one that hit Tunguska in 1908, I believe that was only about 70 or so kilometers across. So, or no, excuse me, 70 meters, not 70 kilometers. That would be much worse if it was 70 kilometers. 70 meters. And that one caused, a massive explosion that was, heard all over Russia. And fortunately, the area it landed in was just a dense forest, but miles and miles of forest were destroyed there. So if we get hit by a 1 kilometer asteroid, the effects will be quite a bit worse. But of course, this is assuming that in the next 500,000 years, we don't find a way to actually deflect these asteroids or anything like that. But yeah. Then in about 1 million years from now, or sometime in the next million years, the star Betelgeuse will have gone supernova. And of course, you'll notice that whoever made this picture here clearly didn't take into account that proper motion of the stars that I talked about before, because as you can see, Orion is still sort of looking the same. Yeah, the person who made that picture was me. But so Stellarium, the software I used here, actually can't go 1 million years into the future. It can only go about 100,000. Oh, and also, if you'll allow me a tangent, I have a story about this too. When I fired up Stellarium to take this screenshot, I actually saw a very bright moving point of light in Stellarium, and I was like, huh, that's weird, that's not usually there, and it was extremely bright. So I clicked on it, and it turns out it was actually showing me at the time that I was looking at it that there was an iridium flare happening overhead. And it was about like -4 magnitude or something like that. So I was like, oh wow, but as I saw it on the screen, it was very quickly dimming, and so I would have seen an iridium flare if I was outside looking at the actual sky instead of the virtual sky. But I digress. So anyway, well, probably about 1 million years from now, also, there are 2 moons of Uranus called Desdemona and Cressida. There's some of the inner moons of Uranus, and it turns out these moons aren't particularly stable. So their orbits probably in the next million years or so will cause them to collide with each other. If Desdemona doesn't hit Cressida, then it might hit another moon called Juliet of Uranus. But yeah, that may happen. And also, in about 1.4 million years, the star Gliese 710 will have a very close encounter with the Sun. So right now, the star Alpha Centauri is about 4.5 light years away from us. And this star, when it gets close to us, will actually be about 1 light year away from us at its most likely distance here. That's about 0.3 parsecs, which is just about 1 light year. So that'll be brushing up against the edge of the Oort cloud, and that may cause several comets to come flying into the inner solar system. Should be a pretty good time for comet hunters, as long as they don't come too close to the Earth. But yeah, that'll happen, and eventually, of course, it's going to go on its way and recede again. And then in the next 10 to 1 billion, 10 million to 1 billion years, we have more moons of Uranus colliding with each other. These ones, Cupid and Belinda, more inner moons of Uranus that are also going to collide sometime. And in 50 million years, we have yet another collision. The moon Phobos, which is the largest moon of Mars, it looks like this, is sort of a doomed moon because it's spiraling inward towards the planet. And in about 50 million years, it's going to collide with Mars. We're not sure if it's going to go down in one piece or if it's going to break up into a bunch of little asteroids and then pepper the surface that way. But 50 million years from now, Mars will be left with only one moon instead of two like it has right now. And also in 50 million years, plate tectonics will have been happening. Of course, they're happening all the time. But what's going to happen then is that the African plate here is going to move up and collide with the Eurasian plate. And what that's going to do is it's going to close up the Mediterranean basin here. So instead of having a large sea right here, you'll have a mountain range, kind of like the Himalayas are right now. And maybe bigger, yeah. And in 100 million years, it's likely that Earth will have been struck by one of the dinosaur killer size asteroids. Again, assuming we cannot deflect those by this point in time. So we better hurry because you know what it did to the dinosaurs. We don't want that happening to us as well. And also in 100 million years, you have something?
How big was that one?
The dinosaur killer one? I don't remember exactly. 6 miles. Okay, yeah, so about like the size of a small mountain, I guess. Yeah. So yeah. And then in 100 million years, the planet Saturn will actually no longer have any rings. It might look like this, which is kind of weird to look at now because we're so used to having the rings around it. But 100 million years, the planet Saturn will no longer have any of its rings. And in 180 million years, the moon will have worked its magic on the Earth enough that the day will now be 1 whole hour longer than it is right now. So eventually it'll be 25 hours a day instead of the current 24. And in 240 million years, huh?
Will I get overtime?
Hopefully. And in 240 million years, the sun will have made one complete orbit around the Milky Way. So that's sort of the end of the near future events. Yes, believe it or not, 240 million years is near future compared to some of the things we'll be talking about in just a few moments. So in 500 million years, it's likely that a hypernova will have occurred within 6,500 light years of the Earth. And a hypernova is basically just a extremely bright supernova, like 10 times or more the normal luminosity of a supernova. And if it's angled at the wrong direction, then the gamma ray burst that accompanies it may hit the Earth, and that could be a danger to life on Earth if we haven't already been destroyed by many of the other things I've been talking about so far. And in 600 million years, this is really bad news, we won't have total solar eclipses anymore because basically as the moon is slowing down the rotation of the Earth, it's also moving further away. It only moves like a few centimeters away from the Earth each year, but in 600 million years, it'll move far away enough that we'll only have partial and annular solar eclipses, so this will be a thing of the past then. And also in 600 million years, the sun will have started to get a bit brighter, and as it does so, it's basically going to change the carbon silicon, I believe, cycle of the Earth, which will mean that a lot of carbon dioxide will start to get trapped in the rocks on the surface, and eventually it'll get to a low enough point that photosynthesis, C3 photosynthesis, which is what 99% of the plants on Earth use, will no longer be possible. And that's going to have very bad effects for all the entire ecosystem. And then in 800 million years, C4 photosynthesis will no longer be possible. That's the other 1% of the plants. So at this point, all multicellular life on Earth will die out. So only single-celled life will remain at this point. And in 1 billion years, the Earth's oceans will have boiled away due to the increasing, getting ever brighter and ever hotter sun. In 1.3 billion years, eukaryotic life, which is all life that has a nucleus in its cell, will no longer be able to survive. And in 1.5 billion years, the sun's habitable zone will have moved out enough that Mars, surface temperatures on Mars will actually be sort of akin to those on Earth during the Ice Age. So it'll actually be quite a bit warmer than it is right now. And in 2.3 billion years, the Earth's outer core will solidify and freeze, basically, and that will shut down the magnetic field, which is what keeps all those, most of that harmful solar radiation and solar particles away from us. So those are going to strip away what's left of the Earth's atmosphere. And in 2.8 billion years, no form of life as we know it right now will be able to survive on the Earth at that point. But there's still a lot more to go from there, because that's just our solar system, or that's just the Earth really, and there's still a lot happening in the rest of the solar system and the rest of the universe. In about 3.6 billion years, Triton, which is the largest moon of Neptune, will fall through the Roche limit, which is basically the point where the moon gets so close to the planet that the planet's gravity itself is stronger than the moon's gravity that's holding it together, and that basically causes it to break apart and form a ring system. So in 3.6 billion years, Neptune will have the best ring system, since Saturn's will be long gone. And in about 4 billion years from now, the Andromeda Galaxy and the Milky Way will collide with one another. And scientists have dubbed the new merged galaxy Milkomeda. So you know what that means. We'd really better put our heads together and think hard on this one, because we only have 4 billion years to come up with a better name than Milkomeda. And about 5.4 billion years, the sun will finally leave the main sequence and become a red giant. And so it's going to expand quite a bit and engulf Mercury and Venus. And possibly in about 7.5 billion years, it might engulf the Earth as well. And maybe Mars too. We don't know exactly how big it's going to get. And in 8 billion years, the sun will have cast off its outer atmosphere, and it'll now become a white dwarf, which is just a stellar remnant, basically the former core of the star, no longer undergoing any nuclear fusion. It's just going to shine for a long time like this, though, just because it's so bleeding hot from all the energy left over from when it was actually doing nuclear fusion. Then, big jump here, in 100 billion years from now, the universe will have expanded enough that all the galaxies that were outside of our local group will no longer be visible. Basically, light has a speed limit to it, and basically if the universe, if it's far enough away and if the universe is expanding quickly enough, then the universe will actually be expanding, making more distance between us and the light than the light can actually go, so it'll actually be sort of moving away from us, kind of. So that means the observable universe will be only these galaxies within our local group. And of course, as I said before, Milky Way and Andromeda will have merged a long time ago. And then in about 450 billion years, all of those galaxies in the local group will have merged together to form one large elliptical galaxy, something like this. And in 1 trillion to 100 trillion years from now, I didn't do that. 1 second. Let's try that again. Yes, so in 1 trillion to 100 trillion years, all of the interstellar hydrogen that's responsible for forming new stars will have basically been depleted. So many stars will have formed that all that hydrogen, or most of that hydrogen, will have been fused to form some of the heavier elements. So what this means is star formation at this point will no longer be possible. And that is the mark of our next transition from our current stelliferous era to the degenerate era. And in the degenerate era, it's called that because basically there are no more new stars forming. Everything that's left over is sort of, degenerating. So in 110 to 100 trillion years from now, all of the stars that are left over will have completely exhausted their fuel, all their hydrogen and helium for nuclear fusion, and we'll just be left with stellar remnants, things like white dwarfs and neutron stars and black holes at this point. So there won't be any actual stars doing nuclear fusion anymore then, but they'll still be, all the remnants will still be glowing again because of how hot they are and how much energy they have left to give off. And in 1 quadrillion years from now, enough stellar close encounters will have happened to basically fling any planets that are orbiting around their stars off into space. So, of course, a stellar close encounter is like what we said before, when two stars in the galaxy come pretty close together and they sort of gravitationally perturb each other. They would also gravitationally perturb any of the planets in that system. And they don't happen, like I said, they don't happen all that often, but we have all the time in the universe here available to us. So eventually, enough of them will happen that no more planets will be orbiting around the stars. They'll all just be flung off into interstellar space. And then, in 10 to 100 quintillion years from now, at that point, all of the stellar remnants themselves will have gone through enough close encounters that they'll be flung out of the galaxies, or most of them will at least. So galaxies will be pretty sparse. So at this point, most of the things in the universe, you won't really have any binary stars or really anything orbiting anything else at this point. It'll just be a bunch of things sort of all on their own in the universe. And in 100 quintillion years, the Earth will collide with the black dwarf sun, which is now a black dwarf because at this point it will have given off all of the energy that it had left over, and it'll just be sort of a dark ember left over. And the reason why the Earth will collide with it, again, this is assuming the Earth was not previously consumed by the sun during its red giant phase. The reason why it will collide with it is because it turns out when things basically orbit each other, they're giving off gravitational waves. And gravitational waves are pretty weak compared to electromagnetic waves, which is what we're used to seeing, like this laser pointer, for example. Gravitational waves are pretty weak, but when gravitational waves are given off by any two objects orbiting each other, they do give off a little bit of energy. So over time, the Earth and all things orbiting the Sun, assuming it wasn't ejected previously as well, will give off enough of its energy that it'll sort of spiral inwards very slowly and eventually collide with the black dwarf Sun. Now, you see, we've gone to scientific notation because we don't really have words or suffixes for numbers these big. In 10 to the 30 years from now, any stellar remnants that were not previously ejected from their galaxies will spiral inwards towards the center of their galaxies, again due to gravitational waves, and they will fall into the central supermassive black holes of their respective galaxies. And then, this is where it starts to get pretty interesting. So some of you guys, also, yes, this is apparently has something to do with this. I don't understand this. I'm just sort of putting it up there. But apparently, it turns out, well, first of all, let me preface this by saying a lot of you are probably familiar with radioactive decay. That is where heavy elements are sort of unstable, and given enough time, they'll decay into less heavy elements and give off things like gamma rays or electrons or alpha radiation. Well, it turns out that protons and neutrons, which are the things that make up the nucleuses of atoms, may also undergo decay. They may or may not. We don't know at this point. But if they do, yeah, if we give them long enough, if they do go through it, they will eventually decay, again, assuming this theory is true. So at that point, if this happens in this unimaginably huge time frame, there won't be any real matter as we know it now left in the universe. We'll just be left with subatomic particles at this point. But this may not happen. And but anyway, at this point, if it does happen, or if it doesn't happen anyway, pretty much all that'll be left in the universe is just black holes at this point. And now, assuming that what I just said before wasn't true, if they don't, if protons and neutrons do not decay, then something also very strange will happen, something called quantum tunneling. And again, this is all very advanced physics that I don't really claim to understand. But basically, there is a small chance, a very small chance, that basically atoms could possibly phase through something else due to quantum tunneling. And this is, again, very rare, but we have all the time in the universe available to us. So given very, very long time frames like this, rare things are bound to happen. So eventually, if protons and neutrons don't decay, enough of this quantum tunneling will have happened that any matter left over in the universe will have sort of rearranged itself into a shiny, smooth sphere, kind of like this. So yeah, and again, assuming protons and neutrons don't decay. And then, this is where it starts to get weird. Assuming, implying it wasn't weird before, this is where it gets very weird. So before I go on and say that, let's say I'm going to have to ask you to accept a very strange and seemingly contradictory fact about the universe. So there is a theory that all around us there are so-called pairs of virtual particles that are popping into existence and then immediately being pulled right back towards each other and annihilating themselves. And this happens extremely quickly. And it just happens all around us, all the time, everywhere. So now that you've accepted that, there's something very, very strange that can happen if these particles pop into existence right near a black hole. Because normally they'd pop into existence and then immediately say, oh, hey, you're matter, you're antimatter, let's destroy each other, and they'd be gone. But if one of them pops into existence on one side of the event horizon of a black hole, and then one pops on the other side, well, one of them's inside the event horizon. And of course, if something goes inside the event horizon of a black hole, it can never get out. So this one is doomed, and it's going to fall right into the center. And the other virtual particle won't be able to annihilate it because it just went into the black hole. So that one actually goes off and becomes a real particle. Now, the other weird thing about this, that's possibly even weirder than what I just said, is that if a particle like that, a very small mass, just appears inside the event horizon of a black hole, it will actually decrease the mass of the black hole. Not increase, decrease. Now, this doesn't happen for most things because when they're falling into the black hole, they have quite a bit of kinetic energy. So when they eventually get to the center, basically that kinetic energy gets converted to mass, and it results in a net increase in mass, as we'd expect, but not for these things, which pop in and have no velocity. So they actually decrease the mass of the black hole, and so that means over vast, incalculable periods of time, black holes will actually evaporate. So even they are not going to last forever. So you see, we're getting into from the very big to the mind-bogglingly large numbers here. So in 5.8 times 10 to the 68 years, a 3 stellar mass black hole will actually completely evaporate due to this process, which is called Hawking radiation, of course named after Stephen Hawking, who was the one who proposed it. And what happens as it gets smaller and smaller, as more of the black hole evaporates from these virtual particles, is that the evaporation as it gets smaller will actually speed up. So smaller black holes will actually evaporate faster than larger ones. And since there is some actual radiation coming off, since there are particles being sort of spawned right outside of the event horizon, and as this speeds up as the black hole gets smaller, what this means is when a black hole is getting close to its end, it'll actually start to glow. So it won't really be black, or it won't look black anymore from the outside because of all these virtual particles spawning into existence right outside it and giving off their radiation. And of course, the smaller it gets, the faster it evaporates and the brighter it gets, until eventually, right at the end, it basically just explodes. And that's the end of the black hole. But even in this very dark time of the universe, I mean dark literally because there aren't any more stars or anything like that shining, there will be brief periods where black holes will light up certain parts of the universe as they die, and then eventually they'll explode and things will get dark again for a really long time. But anyway, that's how long it takes for a 3 stellar mass black hole to evaporate. Now, for ton 618, which is the largest black hole that we know of right now. It's going to take this long, which is much, much, much longer than this. By the way, if you don't know what scientific notation is, basically these little exponents here, that's how many zeros would follow this 10 here. Really, that's including this 0 as well. So we went from 68 zeros here to 99 zeros for how many years it's going to take for the largest black hole known to evaporate via this Hawking radiation process. And once that's done, oh yeah, we have far more than 20. We have well, I couldn't say it properly because I don't have enough time in the universe left to say the number of zeros that it'll take. So once all the black holes have evaporated, then we now enter the second dark era of the universe. Of course, the first one was right before stars formed. So the second dark era, there is another chance that something weird is going to happen. There's a theory called a false vacuum, which basically states that all of the fields, like the electromagnetic field, the gravitational field, all these fields have reached their lowest energy state and are stable, with the possible exception of something called the Higgs field. And that might actually be in something called a false vacuum, or false a metastable state, as it's called, where basically this is sort of a graph of how low the energy, distribution of that field. And you see, this is the true lowest point, but it's possible that the Higgs field may have found a false lowest point here, where it's sort of in a somewhat stable state, but really it could go quite a bit lower. And if quantum tunneling happens just the right way, then it's possible for the Higgs field here to actually escape and go down to the actual true lowest state. And if that happens, it would be very bad for anything near it, because basically all the laws of physics around it could change, and anything around it would be blown to smithereens. Of course, at this point, all life in the universe would really be gone, so there was nothing really nothing in danger.
Especially if it was a Higgs field, and then
Yeah.
propagate across the entire universe.
Yeah. Well, actually, if the universe expands quickly enough, it may not have time to actually reach the other parts of the universe. But yeah, in 10 to the 139 years, if there is a false vacuum, which we don't know if there is, but if there is one, it will probably have, decayed by now, or collapsed. And then, in 10 to the 1500 years, once again, assuming that protons and neutrons do not decay, at this point in time, basically random collisions between atoms will have caused all matter in the universe to fuse or decay into iron-56, which is basically the most stable atom imaginable. So at this point, assuming nucleons don't decay, all leftover matter will be iron. And now you see we've gone to multiple levels of exponents here. If there's still matter left over from any stellar remnants or something, enough quantum tunneling will have happened again to turn it all into things like neutron stars, which will eventually turn into black holes, and again, assuming no nucleon decay. And at this point, of course, it'll take those black holes an unimaginably long time to decay, but compared to the oppressively, mind-bogglingly long timescales we're talking about here, this amount of years for these black holes to decay might as well be instantaneous. And then, in 10 to the 120 years, at this point, nothing will be happening anymore in the universe. Basically because if you guys are familiar with entropy, you may have heard that entropy is always increasing to a maximum. So for any closed system, basically the total energy will always try to sort of spread out to its lowest possible state. And the universe itself is one such closed system. So over extremely long periods of time, basically it's going to spread out and become its lowest energy configuration. And so once this happens, nothing will happen for an extremely, extremely, extremely long time. Until maybe this happens. We've gone to 3 levels of exponents now. It is possible, it's theoretically possible, that quantum tunneling that we talked about before may actually trigger a new Big Bang. over unimaginably large timescales like this. If that happens, then maybe a new universe would be born, and maybe stars would form again, and maybe that one would have life as well. So, this is all a lot of gloomy stuff, talking about the end of the universe and how there's just going to be a lot of boring nothingness for the vast majority of the future. But it's possible that there may be new universes that would eventually be formed. So really, that is the end of my talk. So if anyone has any questions, I'll try my best.